All right, now that we know there are these things called Lewis dot structures and we know how to draw them, what do we use to describe their shape? Well, shape matters a lot. Okay, shapes are going to be what determine how our odors are all interpreted. Does something smell sweet or sour or bitter? It's the shape of the molecule that actually determines that. Okay, you don't need to know these are just examples, but there are 7 primary odors that we can ascertain with our olfactory senses, our nose. A musky, a camphoric, erythral, pepperminty, floral, pungent, and putrid. Okay, so things like perfume and aftershave and mothballs and pears and menthol and roses and vinegar and rotten eggs, those are all a wide variety of smells. Okay, each one of the molecules that is responsible for that smell has a different shape, and it's kind of like a lock and key inside your nose. So if this is your nose and those are your nostrils right here underneath your nose, okay, the smells go in and they trigger into some receptor, and that receptor goes up to your brain and says, this is what you should be smelling. Okay, it's really kind of amazing if you think about it. All right, so in honors chemistry, we do a lab later on where we start to make different kinds of scents, and you'll see things like jasmine or peppermint or apple that have like a really good, nice scent, have special shapes to them that are different than the bad smells, like a skunk smell or even like a marigold doesn't smell that good. But you'll see that these smells are definitely responsible for, or the shapes are definitely responsible for the smells. All right, so what determines the shape? Well, the things that determine the shape, again, are the electrons. Okay, the unpaired electrons around that central atom that is bonded together makes a three-dimensional shape. Okay, so stop thinking flat. We are not talking about flat stuff. We're talking about three-dimensional. No flat earths. We're talking spheres, not circles. Okay, and all of these atoms have these negatively charged electrons. And what do electrons do? Electrons repel other electrons. So the whole goal of this whole thing for these shapes is that all these things want to stay as far away from one another as possible. Okay, they all want to repel one another and be as far as possible from one another, which is where we get valence-shell electron pair repulsion theory, or VSEPR for short. Okay, VSEPR means that these electron pairs are going to maximize the space around them. They are going to repel and be as far away from one another as possible. So it's going to depend on a couple of things. It's going to depend on the number of atoms or electrons around the central atom and what kinds of things are bonded to them. Okay, so we are going to specifically look at 2 terms. One's in your book, one's not. Bond angle, which is the angle of the bond. So this would be the central atom, and this would be one thing bonded to it and another. So this would be about a 90-degree angle. And then this term right here, you should star circle highlight, steric number. It's the number of substances around the central atom. It can be a bond or a lone pair, and most people forget that it could be a lone pair. So definitely star that as well. So you'll see that one important thing that we distribute in class is going to be this VSEPR geometries chart. Okay, the one that I give you is marked up a little bit. If you don't have that one, it's okay. You are going to be responsible here in class to know 2, 3, and 4 things around the central atom. These 5 and 6 are for AP chemistry. Okay, steric number means the number of atoms and lone pairs around the central atom. And then you'll see up at the top, it'll tell you how many lone pairs we're talking about. So you max have to worry up to 2 lone pairs. All right, so you'll see E. E is going to be the central atom, and X is going to be the bonded atom. Okay, so here we have one thing in the middle and 2 things bonded to it. What's as far away as 2 things can possibly get from one another? That would be 180 degrees, or on the complete opposite sides of one another. And it would be a linear shape. Okay? 3 things around a central atom, that's going to be maximum 120 degree angle. And it would be called a trigonal planar, where all 4 of these things are in the same plane. Okay, if one of them is a lone pair, it takes out one of the available things for bonding. But this still has a negative charge, so it's going to push down on the 2 other things bonded to it. So that means, bonded to the central atom. So that means it's going to be slightly less than 120 degrees. Whenever you have a lone pair, it's slightly less than the original angle. And that's going to be called a bent or angular shape. The 4 things around the central atom, 1, 2, 3, 4, is called a tetrahedral shape, and it has a bond angle of 109.5 degrees. If you have one that's printed out and doesn't say that 0.5, please add that in. But that's as far away as these 4 things can get from one another. It is not in a perfect T. That's only 90 degrees between everything. Here you see the shifting with this wedge shape. Some things are going to come in front, some things are going to come in back, and it's actually going to maximize the amount of space around it. And it's going to make this 109.5 degrees, which is bigger than 90 degrees. Okay, if one of them is going to have a lone pair on the top, it's going to push down on the other 3 things bonded to the central atom. So the bond angle will be slightly less, or 109.5 degrees, and be a trigonal pyramidal shape. And if it has 2 lone pairs, it's going to push down even more and be much less than 109.5 degrees. And the specific bond angles will depend on what the electronegativities are for all of your atoms. So let's take a look. Okay, so starting off with 2 things around the central atom with no lone pairs. Okay, you can have beryllium in the middle and 2 chlorines around it. The maximum distance that can be between them is going to be 180 degrees. You can have carbon dioxide, carbon and 2 oxygens on either side. It doesn't matter if it's a single bond or a double bond, it's still going to be 180 degrees. Or you can have your hydrogen cyanide, HCN. Okay, the maximum that these 2 things can get away from one another is 180 degrees. Okay, 3 things around the central atom is going to be a trigonal planar, and that is going to have a bond angle of 120 degrees between it. Okay, so BF3, you have boron trifluoride. You have 3 things around it. Since this one doesn't have any lone pairs, so you're going to see that it's going to puff out like that. Boron trihydride, same thing. And then we see our SO3s, where it actually has some resonance. And you'll see that sometimes we have the bond angle, double bond here, here, and here, but there's 3 things around the central atom, always 120 degrees around them. Okay, if one of those things is a lone pair where you do have, okay, that this lone pair right here is going to push down on the bond angle, and instead of being 120, it's going to be slightly less. So it gives you this bent or angular shape. SO2 gas does exactly this. Okay, 4 things around the central atom, no lone pairs. That's going to be your tetrahedral shape, 109.5 degrees. Methane, CH4, you'll often see to show that something is going towards and away. You'll see the wedge coming out towards you and the dash going away to kind of show that three-dimensional version of the whole thing. Um, Dichloromethane or silicon tetrafluoride, um, phosphorus trichloride. This one, they're all going to have 4 things around the central atom. All of them are going to maximize the difference between them. If we take off one of the things around the central atom and replace it with a lone pair, it's still going to maintain that original tetrahedral shape, but the bond angle changes to 109 less than 109.5. So that little tripod looking thing will be a trigonal pyramidal shape. And that's where we have our PF3 or NH2Cl. They're all going to have that bond angle of 109.5 degrees. And if we have 2 things around the central atom and 2 lone pairs, that counts as a steric number of 4. Okay, this will be a bent or angular shape and have a bond angle less than 109.5. F2O, BrO2, SCl2, they all follow that. But the one that I really want you to pay attention to is our water, because we're going to actually get into a whole chapter just with our water and all the capabilities of it having. So water has 2 lone pairs and 2 things attached to it. So it starts with having that tetrahedral shape, but 2 of them are taken out by these lone pairs that are here. These lone non-bonding pairs push down on the hydrogen. So it has a general bond angle less than 109.5 degrees, but specifically for water, it's 104.5, which I believe is a radio station around here. Okay, so water should be easy peasy, and you should always remember its specific one is 104.5. So definitely star circle highlight exactly that. All right, so there again, we have our VSEPR geometries. You need to know linear, trigonal planar, bent or angular, tetrahedral, trigonal pyramid, bent or angular. And you'll notice that these 2 bond angles are different, and you don't need to know these guys down at the bottom. That's for AP.